So here we are going to see how to calculate the heat transfer coefficient for in natural convection as well as in forced convection. So coming to the specifications, so the duct size here is like 15 by 10 centimeters. The diameter of the pin fin, so the pin fin diameter is 1.27 centimeter. Diameter of orifice 2 centimeter. Diameter of the delivery pipe 42 mm, and the coefficient of discharge is 0.64. So now coming to the observations. So what we had observed from the experiment. So you can note down in this tabular column. So first we had performed the natural convection. So what are the fin temperatures we had observed? So one is 205, second one is 179, and then 147, and then 132, and then 122. And the ambient temperature is 38 degrees centigrade. And the power supplied here is 56.16 watts. So the manometer reading will be 0. So we are not going to use any external device. So we are not having the manometer reading. So it will be 0. So these are the readings we are going to get from the experiment. So now coming to the calculation part. So first we are going to as well as write down the forced convection readings also. So the manometer reading. So what we had observed from the experiment, it is 18. So the difference is 18 mm. Okay. Now the temperature readings are so 173, 143, 1112, 94, 82, and the ambient temperature is 29 degrees centigrade, and the power supplied is 56.16 watts. So now coming to the calculation part. So here first we are going to take the surface temperature. So T1 plus T2 plus T3 plus T4 plus T5 by 5. So for natural convection. So we are going to get the average temperature readings around 157 degrees centigrade, right? So it will be around 430 Kelvin. Now, so after calculating the average temperature, so we need to calculate the film temperature. So that is nothing but surface temperature plus ambient by 2. So the surface temperature here it is 157, and the ambient temperature in the natural convection is 36, sorry 38. So the film temperature will be 97.5 degrees centigrade. So it will be around 370.5 Kelvin. Okay. Now we need to write the properties of air at this film temperature. So properties of air at 370.5 Kelvin. So now for this we need to refer to the data book. Okay. So from the data book, so we are going to get the properties. So new value will be the specific heat 1.0115 kilojoule per kg degree centigrade, and the thermal conductivity of air is 0.003184 watt per meter Kelvin, and the Prandtl number we are going to get 0.6727, right? And kinematic viscosity nu is equal to 23.33 into 10 power minus 6 meter square per second. So these are the properties of air we are going to note down from the data handbook. Okay. Then we need to calculate the Grashof number. So here you can see. So I'm going to do the calculation here. So the Grashof number, the equation is given by G beta delta T LC cube by nu square. Okay. So G is known to us. So the gravitation constant it is 9.81 meter per second square. Then beta. So here you can see how can we calculate beta? So it is nothing but 1 by T film temperature. Okay. So beta is 1 by T film. So already we had calculated the film temperature. So 370.5. So 1 by 370.5 gives us the beta value. Now, what is LC? This is the important one. So LC is the characteristic length. So it is given by, so here you can, I will show you. So here you can see. So the characteristic length is taken as LC is equal to L, right? So LC is equal to L if it is a vertical position. If it is a horizontal position, we are going to get the diameter of the fin. So if it is a horizontal position, we are going to take the diameter. If it is a vertical position, we are going to take the length. Okay. So now we can substitute all the values in this. G is 9.81. So beta is 1 by 370.5 into delta T, surface temperature. What is the surface temperature? Minus ambient temperature, right? So 157 minus 38, right? Next into, so what is the LC? D, we need to take, so here the fin is in horizontal position. So we need to take the diameter of the fin. So it is, so the diameter of the fin is 1.27 centimeters. So convert that into meters. So it will be 0.0127 whole cube by, so what is the new kinematic viscosity is 23.33 into 10 power minus 6, right? So we are going to get the GR value as 11857.7. So this is the GR, and what is the Prandtl number? So already we had taken from the data handbook, 0.6727. So if you multiply these two, GR, PR, right? So we are going to get the GRPR value. So it will be around 8213. 8213.83. So now, after calculating GRPR, so you can see these empirical relations of air for free convection. So GRPR value lies in 10, 0.1 to 10 power 4. So we can use the Nusselt number equation as mu is equal to 1.1 GRPR whole power 1.7. So write down that equation. So Nusselt number is equal to 1.1 GRPR whole power 1.7. So 1.1 into GRPR is 8213.8 whole power 1.7. So the Nusselt number value we are going to get 3.98. So this is the Nusselt number value. So already we know the equation Nusselt number is equal to, so you can see here. So Nusselt number is equal to HLC by K. So Nusselt number is equal to HLC by thermal conductivity of air. So Nusselt number is 3.98. So H we need to calculate, and what is LC? So it is D. So 0.0127 diameter of fin by, what is the thermal conductivity? So 0.03184. So if you calculate the heat transfer coefficient, we are going to get H is 9.97 watt per meter square Kelvin. So this is the heat transfer coefficient from pre-convection. Now we need to calculate. So heat transfer coefficient we had calculated. Now we need to calculate the fin efficiency, right, in natural convection. So what is the fin efficiency? So that we can calculate by using equation Q is equal to root over HPKA into Ts minus T infinity into hyperbolic function tan H of ml. So this tan h is the hyperbolic function. Okay. So now here we know perimeter P is equal to pi d, area pi by 4 d square. So you can calculate all these values. So perimeter we are going to get 0.398 and the area so 1.266 into 10 power minus 4. Okay. Again we can calculate m value. So the small m is equal to root over hp by ka. So this value will be around 5.337. So these equations you can see here. So fin efficiency, to determine the fin efficiency, you can see Q value, M value, perimeter, area, right? So we had calculated all the values. So now substitute and calculate the Q, heat transfer through the fin in natural convection. So you can substitute all the values in this equation, root over HPKA Ts minus T infinity tan H of ml. So that we are going to get the Q value as 5.877 watts. So this is the amount of heat transfer from fin in natural convection. Now, in order to calculate the fin efficiency, so it is given by tan h of ml hyperbolic function tan by ml. So this is the equation. So if you substitute all the values, tan h of what is the m value 5.337 into, so what is the length of the fin here 15 centimeters. So it is 0.15. So please remember this is L not LC. Okay. So 0 length we need to take. So by m is 5.337 into 0.15. So the efficiency of fin will be 82.98%. So if you calculate, we are going to get the efficiency as 82 point, sorry, 82.98%. Right? This is the calculation part for natural convection. So in the same way, we need to calculate for forced convection. So up to now, we had did the calculation for natural convection, right? So and we had calculated the efficiency. Now we are going to calculate heat transfer coefficient and then we are going to calculate the efficiency in forced convection. So for that you need to use these equations. So first, this is the part for forced convection. So we need to calculate the discharge of air because here we are going to use the blower in forced convection. So we need to calculate the discharge of air. So for that we are going to use Q is equal to CD into A into root over 2GHA. So CD is the coefficient of discharge, area of cross section of orifice, root over 2GHA. So if you substitute all the values in this equation, right? So we are going to get the value QA is equal to 3.447 into 10 power minus 3, right? Meter cube per second. So that is the discharge, right? So now coming to the remaining calculation. So here you can see. So we need to calculate this HW. Okay, H1 minus H2 by 100. So it is 52 minus 34 by 100. So this is the height of the mercury column. So it is 0.018 meters. So if you calculate HA, so it is rho W HW by rho A. So density of water, density of air, right? So if you calculate substitute these, we are going to get the value as 15. So 15 meters. Now coming to this velocity. So U is equal to QA by duct area, right? Into film temperature plus 273 means we are going to convert that into Kelvin and ambient temperature in Kelvin. So if you do this, so QA is, so what is QA? So in the starting, we had calculated 3.447 into 10 power minus 3 by what is the duct area. So if you see the specifications of the duct, so here you can see the specifications, right? Duct size is 15 centimeter by 20 centimeter. So convert that into meters. So that is the duct area. The duct area will be 0.15. So 15 centimeters convert into meters, 0.15 into zero point 0.1 into, so 74.9 is the film temperature. So convert that into Kelvin by ambient air is, so in forced convection the ambient air is 29 degrees. So convert that into Kelvin. So the velocity will be around 0.2647 meter per second. So this is the velocity we are going to get. So U is the symbol we are going to follow. So this is the velocity. Now calculate the film temperature. So the surface temperature we are going to get by doing the average of the temperatures in forced convection. So it will be around 120.8 plus what is the ambient 29 by 2. So it will be around 74.9 degrees centigrade. Okay. So now you can use the Reynolds number, or we can calculate the Reynolds number. So after this, we can calculate the Reynolds number. So in order to identify the Nusselt number equation. So Reynolds number is given by rho u d by mu. So density, velocity, so and then diameter, and then dynamic viscosity, rho u d by mu. So if you substitute all the values, so the density 0.9980, velocity here it is 0.26. So the velocity we are going to get 0.26. Then the diameter is 0.0127 by what is the dynamic viscosity? So 2.075 into 10 power minus 5, right? So if you calculate, the Reynolds number will be 161.68. Okay. Now we can see the equations for Nusselt number. So we are going to have two ranges here. One is between 40 and 4000, and another one is for 4000 to 40,000. So our value lies in first range, 40 to 4000. So we can use this equation. So Nusselt number is equal to 0.683 Reynolds number whole power 0.466, right? So now calculate the Nusselt number. So Nusselt number is equal to, so if you substitute Reynolds number here, the Nusselt number we are going to get, so 161.68, sorry. So it is the Reynolds number, and the Nusselt number you can calculate here. Now, so after calculating the Nusselt number, so we can equate to the HLC by K, right? So from this equation, we can calculate the heat transfer coefficient. So the heat transfer coefficient here we are going to get 17.27 watt per meter square Kelvin. Okay. So once the heat transfer coefficient is known to us, so we can easily calculate the fin efficiency by using the equation Q is equal to root over HP Ka Ts minus T infinity tan HML, and then efficiency of fin is given by tan H of ML by ML. So these two equations are common for both free as well as forced convection. So you can calculate Q is equal to root over HP Ka T surface minus ambient into hyperbolic function tan h of ml. So m is given by root of hp by ka. Okay. So From this, we can calculate Q value. So it will be around 7.026 watts. So this is the heat transfer from fin in forced convection, right? So in order to calculate the fin efficiency, so tan H of ml by ml. So if you calculate this, we are going to get 74.24%, right? So that is the fin efficiency. So in natural convection, we are going to get around 82.98%, and efficiency here it is 74.24%. So in forced convection, we are going to get less efficiency because here we are going to use the extra power to run the blower. So that's why we are going to get the less efficiency. In natural convection, we are not going to use any external devices. So we are going to get more efficiency, 82.98%. So this is how we are going to calculate the efficiency of fin in natural as well as in forced convection.